Hello and welcome to this short video that explains the intuition behind logistic regression. Logistic regression is sometimes referred to as logit. It's a useful tool for prediction tasks and it is sometimes called a machine learning technique. In the YouTube text box beneath this video, you can find the R code that I use so that you can paste it into R and follow the examples and get the same results as me. Okay, so let's start with OLS, a useful benchmark model in regression. We generate 12 data points that correspond to a fictional relationship between relative effort and the score obtained in a test. Looking at the data points, there seems to be a positive relationship. Higher effort is associated with higher scores. OLS regression, short for ordinary least squares regression, finds a best fit straight line to summarize the relationship. The best fit line is a theoretical model that cuts through the data points as well as possible to minimize the distance between the line and the individual data points. We can say that all the predicted values of the data points lie on the line of best fit, and they are represented here by the red triangles. We can also look at the OLS regression output. The coefficient on effort is positive at 3.483. This coefficient is statistically significant, and we can see that by looking at the t-statistic, which is 2.758, and the p-value, which is 0.0202, far lower than the usual threshold of 0.05, and also the significance star indicates that the coefficient is statistically significant at the 5% level. We might also be interested in the indicators of model fit. The R-squared statistic is 0.4321 and the adjusted R-squared statistic is 0.3753. The way to interpret this regression coefficient of 3.483 is that each time that effort increases by 1 unit, then the test score is expected to increase by 3.483. No matter whether you are at the bottom of the range of effort or the top, there is a constant relationship between effort and test score. The straight line means that wherever you are, if effort increases by 1 unit, then we would expect an increase in test score by the same amount, which is 3.483 units. Let's plug these values into our OLS regression equation. Y equals alpha, the intercept term, plus beta times x. X corresponds to the explanatory variable, which is effort, plus the residual error term. So in our case, the test score is predicted to be 59.448 plus 3.483 times by effort, plus the error term, which is 0 on average, so we can just ignore it here. When effort equals 0, test score is predicted to be 59.448. When effort equals 1, test score is predicted to be about 62.9. Now we move to model 2, where we have a binary variable, pass or fail. A test score of 60 or more is a pass, and a test score below 60 is a fail. OLS regression works less well with dependent variables that are binary. Instead, logistic regression is designed for cases where the dependent variable is binary. Let's start by trying to fit an OLS regression to this data and see what happens. A first look at the data suggests that the data points only take values 0 or 1, and they don't seem to line up on a straight line. We can add an OLS line of best fit here, but it looks a bit weird because it does not fit the data so well. The red triangles correspond to the theoretical predictions from the OLS model. We can also see some nonsense predictions at extreme values of effort. The predicted probability of a pass is negative at the lower end of effort, which technically makes no sense because a probability should not be negative. At the upper end of the range of effort, some predicted probabilities are greater than 1, which is also a problem. Ideally, the predicted probabilities of a pass should all lie between 0 and 1. Now we move to model 3, which is estimated using logistic regression. Logistic regression is similar to OLS regression, but it takes a different approach because it does not try to fit a straight line, but a logistic curve that looks like this. As such, logistic regression avoids the problem of making predictions that are below 0% and greater than 100%. However, this comes at the cost of having a best fit line that is not a straight line, but a curve. Here we see some red triangles that correspond to the predicted probabilities of a pass as calculated by logistic regression. With OLS and its line of best fit, which is straight, every time the explanatory variable effort increases by 1 unit, there is the same expected change in the outcome. With logistic regression, the relationship between effort and pass is non-linear. For 1 unit change in effort, the corresponding change in the probability of having a pass is not constant, but depends where you are on the range of the variable. For 1 unit change in effort, the corresponding change in the probability of having a pass is not constant, but depends where you are on the range of the variable effort. This makes logistic regression more of a pain to interpret. Let's look at the regression equations for OLS and logistic regression. With OLS, the dependent variable y depends on an intercept alpha and a coefficient multiplied by the explanatory variable x. The function f is very simple in OLS. It is just a linear relationship. The simple linear relationship means that every time x increases by 1 unit, y is expected to increase by a constant amount. Logistic regression is also a function of the intercept term alpha and a regression coefficient beta multiplied by x, but the function f is way more complicated. Instead of being a linear regression model, logistic regression uses something called a logit link function, which is shown here. The relationship between x and y is non-linear. If x increases by 1 unit, the change in y is not constant but varies. As we will see, the way to interpret logistic regression coefficients is more complicated. So let's take a look at the output for model 3 when estimated by logistic regression. We get a coefficient of 4.7923, which is not actually statistically significant because the p-value is 0.119 above the usual threshold of 0.05. Bummer. This could be because our sample size is quite small. Maybe we could be satisfied instead that it is statistically significant at the 15% level. Anyway, how should we interpret the coefficient? We could plug our estimates of alpha, minus 0.4072, and beta, 4.7923, into the regression equation. When x equals 0, then we get a predicted probability of 0.40 for y. When x equals 0.5, we get a predicted probability of 0.88 for y. And when x equals 1, we get a predicted probability of 0.99 for y. Note that we make the same change to x, adding 0.5 each time, and get very different outcomes for y. We refer to this as non-constant marginal effects of x on y. Logistic regression does not have a straightforward linear relationship between inputs and outputs like for OLS linear regression. Let's go back to the OLS model. If we increase x by 1 unit, then y increases by beta. What is the corresponding expression for logistic regression for how an increase in x translates into an increase in y? Technically, we can rewrite things to say that logistic regression is a linear model for log odds, where the odds are p divided by 1 minus p. So if x increases by 1 unit, then log of p divided by 1 minus p increases by beta. Log of p over 1 minus p is referred to as the log odds, which is the logarithm of the probability of y happening divided by 1 minus p, which is the probability of y not happening. So if beta is positive, then there is an increase in the probability of y happening compared to it not happening. In our case, the value of beta estimated from logistic regression is 4.79, which means that increasing x by 1 unit will increase the log odds by 4.79, which increases the odds by 121. In any case, a positive value of beta increases the odds of y, and a negative value of beta decreases the odds of y, and the precise interpretation of effect sizes is complicated, more complicated than for OLS. Logistic regression also differs from OLS in terms of the model goodness of fit. OLS gives us the well-known R-squared statistic, but logistic regression does not do this. One idea could be to look at the AIC, the Akaike Information Criterion, that comes from logistic regression. Another idea is to use an alternative R-squared statistic, such as the Nagelkerke R-squared statistic. This is not part of the standard output for logistic regression, but it can be calculated quite easily. The Nagelkerke R-squared is calculated in the R code in the text box below this video. So let's consider how OLS and logistic regression would answer the following question. What happens if effort is increased by 1 unit? The OLS answer is straightforward. It increases the probability of passing by 42 percentage points. That's easy to see because the regression coefficient was 0.42. The logistic regression answer is more complicated and less intuitive. There is an increase in the logarithm of the odds of passing that is equal to 4.79. There is something of a debate between econometricians regarding OLS and logistic regression. OLS applied to cases of a binary dependent variable is referred to as OLS LPM linear probability model. OLS has the advantage that the results are easier to interpret in terms of the marginal effects, how a change in x is associated with a change in y. If x increases by 1 unit, how is y expected to change? A drawback of OLS is that it can potentially generate nonsense predictions, such as negative probabilities or probabilities above 100%. But if we are not too bothered about these cases where OLS can sometimes generate nonsense predictions, then we might prefer to keep using OLS because it's easier to interpret. And that's all from me. Thank you for listening and have a nice day.